Hello everyone. This is lecture 11, and as I told you in the previous lecture, I will have some application related to test statistics and NOAA. Um, okay, I did lecture you the ANOVA from the book I am following for business statistics, and today I have some different sources, the different information related to ANOVA, which is similar, a bit different, but I want you to read in different perspective of the ANOVA from different sources. Those are lecture notes you may read from different view to understand the ANOVA procedure. This is a summary from different sources. And the null hypothesis, if you have four different groups, in fact, you should have, you could have more than four different groups. But here in general, let's say you have four different groups. That's how you construct the null hypothesis. And the alternative hypothesis, which is different from the previous lecture, it is more or less like the way I am teaching for the alternative. At least one is not equal, will be different. That's what it means. So it is different from the alternative hypothesis that is constructed in the previous lecture. Okay, the test, so let's say you have K groups. In the previous week, in place of K, we had T. So K is okay for this lecture. Just consider K is the number of groups, and that's the F statistics you use within the ANOVA table. And this is the F statistics, okay, within the ANOVA table. Okay. This is the note. I want you to pay attention on the note because there are some assumptions related to the ANOVA. You definitely need to satisfy the variances equality. If the variances are not equal among groups, you're not able to use the F statistics of an ANOVA. ANOVA is a parametric statistics that requires the assumption of variances equality, and also you also need to guarantee that the data set has normal distribution. So those two assumptions are very essential for the ANOVA test statistics. If one of the assumptions is violated, is not guaranteed, then you definitely move on to another ANOVA procedure, an alternative ANOVA procedure, which is called non-parametric test statistics. The name is Kruskal-Wallis test statistics. Maybe in the last lecture I will mention about the Kruskal-Wallis test statistics. Okay, you may read yourself all these. The note is very useful. Just please read all this stuff in here. Leave it for you. So this is a graphical representation of the F distribution for the degree of freedom for 3 and 36. This is good. As a good example for showing the picture of the picture of the diagram of the F distribution. Remember, the normal distribution was a picture in a way like this, and the F distribution does not have this picture. See that this is like going that way, and in fact it is the right tail distribution, the F statistics. The first degree, when you increase the first degree of freedom, that one you increase it for a bit and the picture becomes that shape. It's still this picture is still not symmetric. But if you have the degree of freedom very large for the first one and the second one, And you may observe such picture. It's still a bit skewed distribution, but it is very close to symmetric distribution. So this is a good picture. Just I wanted you to see that picture. Okay, this is the ANOVA procedure for this source. According to this source, um, we didn't use this one as SSB. This is the sum of square of between treatments. So we use it to have SSTR. So this the same meaning. And we use in place of K, we use T in our lecture, the previous lecture. N is the same, we use it. This is the whole sum of the number of the number of observations. The mean square between, we use it to have it as mean square treatment. So this is what it means. So it has the same meaning. This is the mean square of the error. So it is the same. So the F statistics is the dividing mean square between two mean square error. Okay, this is very similar. Some description are a bit different, and you can easily distinguish the difference, and you can easily understand that this ANOVA procedure is the same as the previous lecture from different source. So I wanted you to read all this stuff from different perspective, from different sources, which is very much similar. So now, as I told you from the previous week, we will study some example, two example I have today, and I want to explain those two examples in detail. Okay, the first example, this is a good example. Okay, let me read you this example. It's a nice one. Although it's not related to biostatistic, it's not a business statistic. It's more like a biostatistic example, but it is a good example, and I am sure you will understand the ANOVA procedure in different field of science. Let me read you this example. A clinical trial is run to compare weight loss programs, and participants are randomly assigned to one of the comparison programs and are counseled on the details of the assigned program. Participants follow the assigned program for 8 weeks. The outcome of interest is weight loss, defined as the difference in weight measured at the start of the study baseline and weight measured at the end of the study 8 weeks, measured in pounds. Three popular weight loss programs are considered. The first is a low calorie diet, and the second is a low fat diet, and the third is a low carbohydrate diet. For comparison purposes, a fourth group is considered as a control group. Participants in the fourth group are told that they are participating in a study of healthy behaviors with weight loss, only one component of interest. The control group is included here to assess the placebo effect, weight loss due to simply participating. So placebo effect, that means people who are taking this taking something to lose weight does not have anything else, or people who are not preferring any diet program to lose weight. So in total, a total of 20 patients agree to participate in the study and are randomly assigned to one of the four diet programs. Weights are measured at baseline, and patients are counseled on the proper implementation of the assigned diet, with the exception of the control group. Okay, so this is not a diet actually. This is people who are not assigned to any diet program. After 8 weeks, each patient's weight is again measured, and the difference in weight is computed by subtracting the 8-week weight from the baseline weight. Positive differences indicate weight losses, and negative differences indicate weight gains. For interpretation purposes, we refer to the difference in weight as weight losses, and the observed weight losses are shown below. Okay, let me read you this output. Okay, um, there are 5 people assigned for the first group, and the first group of diet low calorie. Those people are taking the diet program for as low calorie. Okay, the first person has lost 8, you may say 8 units. This is 8 units, could be 8 kilograms, 8 pounds, or 8 stones, or 8 hours. uh, this is a different measurement. Let's say you may call it as 8 units. And the second person has lost 9 units in 8 weeks, and the third 6, 7, and 3. So using low calorie diet for 5 people seems to be successful for losing weight. Since it is positive, it means they are losing weight. For the low fat program, it is different from the low calorie. They don't have a fat oil in the food. They eat probably as much as they can, but they don't place the fat inside the food. So those 5 people, after 8 weeks, the first person has lost 2 units, or 2 kilograms, 2 pounds, or something, and the third one is 4. The third one is third. The fourth one is 5, and the last one is 1 unit. Okay, and another diet program is the low carbohydrate program. So those people who are participating in this diet program looks very much similar to the weight loss in low fat. So the first person who are applying low carbohydrate is losing um, three 3 units, and the second one is 5 unit, and the third one is 4, and the fourth one is 2 units, and the other one is 3 units. And the control groups, people who are not taking any diet program or not assigning or a fake diet program, probably the first person has lost 2 units of weight by chance, and the second one is 2 unit after 8 weeks, and the third one, look at that, is negative. It means a weight gain at 1 kilogram or 1 unit weight gain implemented by the third person in the control group. And the third person didn't put weight or didn't lose weight, so it is 0, so no difference between the measurement of weight. And the last person has lost 3 units of weight in the control group. But it is clearly that the control group seem to be, but it's not statistically, we don't know whether it is statistically significant. It is different from the low carbohydrate, low fat, and it is very much different from the low calorie. You can read it easily yourself from the table. Of course, in practice, um, 20, 20 people is not enough to apply the ANOVA. It is because the data set we use, 20 for 20, will definitely do not show Gaussian distribution. This is one of the most required assumption for the ANOVA. But this is not an example to just control to check whether the data set is having a normal distribution, whether the data set have homogeneity of variances. This is not an example. So this is why we pick up only few numbers to understand behind the calculation of the ANOVA test statistics. So the question is, you can now understand what the question is. Is there a statistically significant difference in the mean weight loss among the four different diets? So that's the question. Okay, let's run according to the source. We will run the ANOVA using the 5-step approach. Step one, as I told you in the previous lecture, I always begin with constructing the null hypothesis and the alternative. So since the alpha level is not given in the question, so you may pick up the universal alpha level, so which is 0.05. Okay, the alpha level is 0.05. You always, as I told you, pick up alpha level to be 0.05. So we have four treatments, four different groups. Mu1 equals mu2 equals mu3 equals mu4. And the alternative, the mean weight loss are not all equal. It means are not all equal, that it means at least one diet program is different. Okay, this is my construction of the alternative hypothesis, which is very close. The expression is very close, means are not all equal. Okay, the test statistics, as I told you, we use the ANOVA for comparing at more than three groups, three groups. If you have two independent groups, so the independent t-test is fine. But if you have more than two groups, you definitely need the ANOVA F statistics. So which is the mean square of treatment. So this is between in here, which is the same as the previous one I showed you in the last lecture. And you divide it by the mean square of the error. Okay. To find the critical value from the F distribution table, I already presented you in the previous section. We'll go have a look at for the critical value. Since we have four different groups and T or K is 4, the first degree of freedom is, which is K minus 1 becomes K minus 1 becomes 4 minus 1, which is a 3 for the first degree of freedom. And the second degree of freedom, this is for the degree of freedom between mean square between. And this one is for the denominator part of the F statistics, which is the whole number of observation, which is 20. And you subtract the number of groups or the number of treatments, which is 4, and this is becomes 16. Okay, so see that this is 16. The critical value, which is 3.24. Let's see how this is obtained. And I'm gonna go back to the F table, F distribution table in the previous week, and you will have it on your lecture notes. See that this is alpha level 0.01 and this is 0.05. So what you need first, you need the degree of freedom. This is 3. And you need to look for from this column. Okay, and the degree of freedom for the denominator part, which is 16. So you need to look for this row. So this column and this row, in fact, this is the critical value 3.2389. So if you round it to 2 digits, 2 decimal places, that is going to be 3.24. So I'm gonna go back to my example, speeding up, down. Okay, let's see. We were here. Yes, see that this is justified, which is in my table, the table I supplied to you, which was 3.2389. That's rounded to 3.24. That's the critical value. If the statistics you calculate from this one using the F statistics, and that one here, if this one is greater than 3.24 and you reject the null hypothesis, the equal weight loss, mean weight loss, and you reject it, it means at least one that program is different or more successful or less successful. That's how you conclude in the end. Okay. The group mean are calculated here. For the first 5 people is 6.6, and the second one is 3, and the third one, the low carbohydrate, 3.4. For the control group, the weight loss is 1.2 units. Okay, let's see how it is done for the low calorie. Remember, x1 bar equals 8 plus 9 plus 6 plus 7 plus 3 and divided by 5. Okay, this is divided by 5, and this one is 17, 33, 30, 33, 33.5, and that's 5.5. That's how you get the 6.6. I'm sorry. That's 6.6. So this is 66.10 and 6.6. That's how you get the 6.6 in here. Okay, and 3, and adding up all this for the x2 bar. Let me show you the next one. X2 bar is 2 plus 4 plus 3 plus 5 plus 1 and divided by 5, and this is 7, 9, 10, 15.5, and x2 bar is 3. That's how you get x2 bar. Okay, you see, this is justified, and the other one is similarly calculated. And notice that those are very much similar, probably approximate, and this one is different. This one looks a bit different, and this one is different from the rest. This is my opinion, but we are not really sure. We need to get the F statistics first and check from to check that the F statistic, whether the F statistic is greater than 3.24 to conclude that information. Let's see that. Okay, from the previous week, what we have in place of SSB, we had SS treatment, so which is very similar. By subtracting, this is the X bar. X bar is 3.6. This is the whole mean weight loss. in general, the general mean and the overall mean. Each time you subtract from each group mean from the general mean, overall mean, and square it and multiply it by the sample size. And this is how you get this the the SS treatment, and which is, you can do it yourself and see that this is 75.8. Okay, the error, sum of square of the error, which is very much similar to the one we used in the previous week. So to do that, what you do basically, you try to differentiate from each group its mean and square it and sum all this. So in our case, for the first one is 21.4. This is basically performed by subtracting 8 minus 6.6 to get the 1.4. What you do is 8 minus 6.6 and you get 1.4. And the square of this one is 1.4. The square is actually 1.96. But if you to round it, this source is rounded to one digit, so it is, in fact, this is 1.96. To round it to a single digit, so you need to have it as 2.0, and this one is the square of 2.4. The square of 2.4 is 5.76. So if you round it to a single digit, it will be approximately to be 5.8. That's how you get 5.8. And this is minus 0.6. The difference, 6 minus 6.6 becomes minus 0.6, and the square becomes 0.36. So round it to a single digit decimal place, you get 0.4. And the rest, you complete the rest, and summing up all this becomes 21.4. That's how you get this value. So this is for the low calorie, but you need to perform this calculation for the low fat as well. But the low fat, the mean is 3, so 2 minus 3 becomes minus 1. 4 minus 3 becomes 1. 3 minus 3 becomes 0. 5 minus 3 becomes 2. 1 minus 3 becomes minus 2. And notice that the sum always 0. Always. Okay, the square, and summing up all this, you get 10. Okay, this is for the second one is 10. The first one is 21.4, and the third and the fourth one we have, of course, for the low carbohydrate, the mean weight loss, which was 3.4. So the first observation, you subtract 3.4, you get minus 0.4. 5 minus 3.4, you get 1.6. 4 minus 3.4 becomes 0.6, and 2 minus 3.4, you get minus 1.4, and 3 minus 3.4, you get minus 0.4. The sum, as I told you, notice that this is always 0. Okay, the square, this one is 0.16 rounded to a single digit, so you have 0.2, and this one is 2.56, and after roundation you get it 2.6, and you complete the rest and take the total as 5.4. So now to get the sum of square between sum of square treatment, I'm going to add up 21.4, 10, and 5.4. So this is going to and then you also have The sum of square for the control group, we have missed that. Okay, the mean was 1.2. 2 minus 1.2 becomes 0.8. 2 minus 1.2, it is again 0.8, and minus 1 minus 1.2, which is minus 2.2, and 0 minus 1 0.2 becomes minus 1.2, and 3 minus 1.8 becomes 1, and 3 minus 1.2 becomes 1.8. And squaring all this and summing up, and you get 10.6. So it means, so the sum of square between, or the sum of square treatment is 21.4 plus 10 plus 5.4 plus 10.6 becomes 47.4. That's how you get this one. Okay, and now let's construct the ANOVA table. This is obtained early, and the sum of square of the treatment 75.8, and the error sum of square, or the residual sum of square, which is 47.4. And the degree of freedom, we have four different diet program, which is 4 minus 1, and the error sum of square, which is the degree of freedom, the whole number of observation is 20, and you subtract the number of groups, which is 20 minus 4 becomes 16, and this is the total degree of freedom. As I told you in the previous lecture, we don't use it in the calculation of the F statistics. But if this is given and you don't have this degree of freedom, what you do, you subtract 3 from 19 and you get 16. So it means this one is 3.3 minus 3 plus 16 equals 19. So this is how it is useful. Okay, the mean square. To get the mean square, what we do basically, we divide the sum of square by its degree of freedom. 75.8 divided by 3. That's how you get 25.3. And this one also, the mean square of error, that is 47.4 divided by its degree of freedom, which is 16, and you get rounding to one digit, that is 3. And the F statistics is the division 25.3 by 3. That's how you get the F statistics, which is very much easy. Okay, in the conclusion, the F statistics is very much large, 8.43, which is much larger than 3.24. We have a statistically significant evidence at alpha equals 0.05 to show that there is a difference in mean weight loss among the four diets. We definitely know that there is a difference. So the highest difference is measured from the low calorie. People who are prescribed the low calorie diet is losing the most of the weight are lost by the people who are taking the low calorie diet, because the mean is at least you lose around 6.6 unit weight loss from the low calorie diet, and low fat you lose 3, and low carbohydrate you lose 3.4. And in the control group, those people are prescribed a diet which does not have an effect on losing weight, but it is still 1.2 units they lost in 8 weeks. This could be by chance, or we don't know. So as I told you in here, the low calorie diet, if there is a difference, a statistically difference, The difference should be the highest difference can be observed from the low calorie and control group. So this people are losing 6.6, and in the control group people are only losing 1.2 units or 1.2 kilograms. So at least this is different. We are definitely sure. But I'm expecting, in my expectation, as I told you in here, that there will be no difference between low fat and low carbohydrate, and there will be a difference between low carbohydrate and the control. We know that, and there will be difference. This is the highest difference between the low calorie groups and the control groups. We are definitely sure that there is a statistically significant difference. We are not sure maybe, but I'm sure yes, the low calorie diet program is, although it is more successful than the other diet because the weight loss is higher, we are definitely sure that the low calorie diet is different from the low fat, low carbohydrate, and the control group. Okay. Okay, that's, let's read the conclusion according to this example from this source. We reject the null hypothesis because 8.43 is greater than 3.24. We have statistically significant evidence at alpha 0.05 to show that there is a difference in mean weight loss among the four diet programs. ANOVA is a test that provides a global assessment of statistical difference in more than two independent means. In this example, we find that there is a statistically significant difference in mean weight loss among the four diets considered. In addition to reporting the result of the statistical test of hypothesis, that there is a statistically means to facilitate interpretation. Statistically significant difference in mean weight loss at alpha 0.05 level of significance. Investigators should also report the observed sample means to facilitate the interpretation of the result. In this example, participants in the low-calorie diet lost an average of 6.6 pounds over 8 weeks, as compared to 3 and 3.4 pounds in the low-fat and low-carbohydrate groups, respectively. Participants in the control group lost an average of 1.2 pounds, which could be called the placebo effect because these participants were not participating in an active arm of the trial specifically targeted for weight loss. Are the observed weight losses clinically meaningful? So it is up to you. Or in my case, yes, it is meaningful. Weight loss is statistically different. In my case, 8 units of weight loss is or 6.6 pound. The measurements, yes, they say pounds. In pounds, 6.6 pounds is more or less about 3 kilograms in 8 weeks, which is very successful, very much successful. Of course, depends on the person weight. If the person is very fat, 3 kilograms does not have any meaning. If the people are in the range of within the body mass index and losing 3 kilograms of weight in 8 weeks, in my case, it is very successful and meaningful. Yes, in my case. Okay, let's have another example. Read another example. It's related to biostatistics, not a business statistics anyway, but it is a good example, and I'm sure you understand it easily. And it is good for you to apply different statistics in different scientific field. Okay, let me read you this example. Calcium is an essential mineral that regulates the heart, is important for blood clotting and for building healthy bones. The National Osteoporosis Foundation recommends a daily calcium intake of 1000 or 1200 milligram a day for adult men and women. While calcium is contained in some foods, most adults do not get enough calcium in their diets and take supplements. Unfortunately, some of these supplements have side effects such as gastric distress, making them difficult for some patients to take on a regular basis. A study designed to test whether there is a difference in mean daily calcium intake in adults with normal bone density, adults with osteopenia, a low bone density which may lead to osteoporosis, and adults with osteoporosis. Adults 60 years of age with normal bone density, osteopenia, and osteoporosis are selected at random from hospital records and invited to participate in the study. Each participant's daily calcium intake is measured based on reported food intake and supplements. And the data are shown below. That's the data. So you have, in contrast to the previous example, we have only three groups: one, two, and three. Three different groups. People from with normal bone density and osteopenia group and osteoporosis group. Okay. Is there a statistically significant difference in mean calcium intake in patients with normal bone density as compared to patients with osteopenia and osteoporosis? We will run the ANOVA using the 5-step approach. Of course, we are expecting, uh, this is my expectation. I am expecting to be the normal bone density is thicker, higher than the osteopenia or osteoporosis. This is from my daily life information, and let's see whether this is true or not. One thing here, just to tell you about this data set. The data set is like with 100,000 the measurements. You can possibly reduce two digits. Like in place of using 1200, you can use only the 12, and you use 10, and use 9.8 and 9, 7.5. If you like, you can use such measurements in place of those all this, and the calculation will be exactly the same. The sum of square between the sum of square of treatments will be exactly the same. If you reduce it, if you divide it each measurement by 100, you should definitely get the same ANOVA table. Okay, this is it. In step one, construct the null hypothesis against the alternative, and you're not given the alpha level, use the universal alpha level, which is 0.05, and we use the F statistics and the degree of freedom. We definitely know that since we have three groups, 3 minus 1 becomes 2, and the number of observation, which is 18. So we have in each group we have 6, 1, 2, 3, 4, 5, 6. So in total 3 times 6 becomes 18. So the sample, the number of observation is 18. I'm sorry. Okay, and the second degree of freedom, which is n minus k, and we know that n is 18, k is 3, that becomes 15. That's how you get 15. The critical value is 3.68. Let me show you how we get it. So you look from the 0.05 F distribution table, the second column, and the 15th row. Let me get back to the F table. You already possess it in the lecture notes from in the previous lecture. Okay, that's the table I need to. So I need to look for within this column and within this row. And so I'm looking for 2 and 15. So that's 3.6823. 3.6823. 3.6823. Let's go back to the example. Okay. All right. Um, yes, 3.60 and 3.6823. You can round it to 3.68. Very much close to 3.60. So the test statistic, if you calculate the test statistic to be larger than that critical value and you reject the null hypothesis. Let's see that. So as I told you, if you divide the observation value by 100, so you will get this, the mean becomes 9.38, 383. So this one will be 8 and this one is 7.15. In my case, if you reduce it by the dividing 100, and you will get the sample means of each group will be less divided by 100 as well. But the calculation becomes simpler by hand. Okay, the sum of square between, or the treatment sum of square, is can be calculated that way. Each time you have this one, you subtract it from the overall sample mean, overall mean, which is 817.8. This is the overall mean, and you subtract it from this one, and from this one, and square it and multiply it by the number of observation within the group, each group. It does not necessarily mean that each group should have equal observation. This could be 6, it could be 12, this could be 9, 7. Okay, you can have it. So this is by chance two example. We have equal sizes, but it is not necessarily required. Okay, in the end, the calculation lead to 152.477. Sorry, this is 152,477.7. The sum of square of the error for this type of data set, it takes time because the digits are very high. You have many digits. So performing the calculation for the first group, you get 130,000 or 23.3, and for the second group you get 240,000, and the third group you get 449,750. So adding up all this, and you end up with 819,833.3. That's the sum of square of the errors. So this is placed in here. This is the error residual sum of square. Okay, and this one is calculated in the previous sum of square of the treatment, sum of square between, and dividing those two, I get the F statistics becomes 1.395. Okay, the conclusion, let's see, is this value is greater than 3.68, that's the critical value. It's not greater, so we do not have statistically significant evidence at 0.05 to show that there is a difference in the mean calcium intake in patients with normal bone density as compared to osteopenia and osteoporosis. The next question, are the difference in mean calcium intake clinically meaningful? If so, what might account for the lack of statistical significance? We were expecting to have a statistical significance. And in the beginning of the example, this was my expectation from my daily life information. We expect that at least for the people who have a normal density will have more calcium in their bones. This is my expectation. What can be go wrong? So it contradicts our daily life information. This could be the reason that you have only six few people you selected randomly, so you need to select more than six people for each group, maybe say 15 or 20 for each group, and then you may satisfy your expectation. Okay, this is actually the end of the lecture. I had studied with you to example the application of ANOVA, and I we are given the announcement this week to declare to you that there will be a midterm examination and a final examination. So the examination, of course, will not be performed face to face in the classroom. So it is up to us to give you either a project or exercise or anything else. It is up to me to evaluate you for the midterm examination. So what I'm going to do is I'm going to prepare some exercises and handing it to you from the DYS system of the university, and I will share the exercises with you within the WhatsApp group we constructed some weeks ago. And I'm expecting you to hand me the answer in a very short time and send me quickly in a very short time. And I would like you to be honest in these days, in these difficult pandemic days, and try to work out the exercises on your own. So it will be a homework in place of the midterm examination, and you'll get 40% from this examination, and you'll get the result by the end of this month, April. Um, we are we are told that to give you a week of time for the midterm examination, but in my case, I will give you only a single day, and I want you to work out those exercises in a single day. If you take a seat in the examination, you are given only an hour. I'm giving you 24 hours, whole 24 hours to work out on your own. I want you to be honest, to do it yourself, not copy from your friend. Sit yourself at home, study yourself, and you have all the lecture notes open. And you can gain the information from your lecture notes. Try to work out the exercise on your own. No need for your friend, and you can do it, perform it easily. You can get 100 easily yourself, and please try to have it yourself. So this is the end of the lecture. I will also write you on the WhatsApp group today to discuss this issue for the midterm examination. Okay, take care of yourself. Take care. Talking to you later. Bye for now.